we're going to be learning about kinetic theory. Kinetic theory can basically be explained in very simple terms if we just take a lot of things for granted. So we're going to make a lot of assumptions in this unit, and we're going to see how things simplify when we make it easy. So you're welcome. First off, we're going to take a statistical approach to kinetic theory. We make four simple assumptions about the molecules in a gas. They are to predict essential features of real gases that are at low pressure and far from their liquefaction points. Step 1. There are a large number of molecules N, each of mass m, moving at random directions, all around at different speeds. So we're saying that the total average energy can be any value, but every individual gas is allowed to be somewhere in the plus or negative side of that value. The molecules are, on average, very far apart. So if you think about the vessel that is going to contain this gas and the actual size of the individual molecule, the molecules are extremely far apart compared to their actual diameter. The molecules obey the laws of classical mechanics and only interact with each other when they collide. So this is our greatest falsehood assumption that we say. So in order for us to work, we can't take a quantum approach to atoms. So we use our classical mechanical ideas, Newtonian mechanics, and everything works out fine. Our last one says that collisions are assumed to be perfectly elastic. We assume them to be of a short duration. So just like two train cars bouncing and heading back in opposite directions, or a bouncy ball bouncing on the floor, all of our kinetic energy is transferred from one to another. Nothing is lost, everything is conserved. All right, so if we just take those four simple ideas and apply them all the time, everything works out great. All right, translational kinetic energy. These are the two equations that we're going to use for this subunit. All right, so the first one over here talks about the kinetic energy of the system itself. And what's important to note is that Ke equals 1/2 mv squared. So over here, instead of V, we've replaced it with this value inside the parentheses here. So we can say for a molecule, the VRMS, or root mean square, is equal to 3RT over M, all under the radical. So that's very important to note. And also in the end, the kinetic energy of the gas, or the energy in general, is equal to 3/2 K, my Stefan Boltzmann constant, times the actual temperature. So we will note that the energy of the gas is directly proportional to the temperature. So that's the key to take away from these two equations, is that the energy, the entropy of the gas, is directly proportional to the temperature, but the temperature, the square root of the temperature, is directly proportional to the actual velocity of each individual gas molecule. If you take the root mean square of the average of all the velocities of the gas inside the vessel. So those are the two key points to take away. So we'll see what a practice problem looks like on the next slide. All right, in order for the root mean square speed of the molecules in a given sample of gas to double, what must happen to the temperature? So we know that energy and temperature are directly proportional, but what does it have to do with the velocity of the gases? Like we said last time, VRMS is equal to the square root of 3 times R, my ideal gas constant, times T, the temperature of the gas, divided by the mass of the gas. So what that means is that in order for, I would have to increase the gas by 4, because it's under the radical, in order for the velocity to double. So what must happen to the temperature? increase by a factor of 4 would be my answer. All right, I think we nailed it today.